Good afternoon, ladies and gentlemen. I would like to introduce Dr. Jimy Dudhia, saying first, be welcome to our university. Dr. Jimy Dudhia has worked on all aspects of atmospheric numerical modeling, being on the development and the community support teams for MM5 and WRF model. His scientific contributions and publications are in the areas of non-hydrostatic dynamics, microphysics, planetary boundary layer schemes, radiation schemes, and land surface schemes. Application interest areas include mid-latitudes and tropical convective cloud scale modeling, hurricane forecasting, regional climate modeling, wind and solar energy, and large area simulation. So thank you very much, Jimy, to come here after a long trip.
Good. Thanks, Franciano, for inviting me here to Santa Maria. It's been my first trip to South America ever, so it's an interesting new experience for me to be here in Brazil. This talk is quite long because I'm trying to cover a lot of subjects. It's not just how the model works. I'm also trying to give you some idea of what physics you need in the model and how that all works, because my area is physics. So I'll talk about these before going on to NCAR'S, which is the new model. I'm talking mostly about WRF and the physics there, but NCAR'S shares a lot of physics with WRF. It has a much fewer options, but it'll have the same ideas in the physics. So this physics part is very general in terms of how each part of physics works. I'll talk about the radiation, the surface of the model, how we deal with the land surface and the PBL, turbulence and diffusion, cumulus polarization, microphysics, and the nudging option. So I'll start with radiation. In radiation, we're trying to deal with multiple processes, including obviously the solar input, the cloud effects on the solar input, the long wave output coming emitted from the Earth, but also impacting and affected by clouds, and the absorption and reflection of the solar input at the surface. So radiation is a lot of processes we're trying to deal with in the numerical model. I'll start with the long wave.
It's okay.
In the long wave schemes, we compute the clear sky and cloudy upward and downward radiation fluxes. We consider the infrared emission from layers. The surface, so it's a layer, one by one layer model. It's one-dimensional effectively for each column. The surface emissivity is based on land type. Usually the surface is close to a black body. Emissivity is not far from one. The flux divergence leads to cooling in a layer, so the infrared is emitted and then it converges or diverges in different layers depending on whether it's absorbed or emitted. So it's a combination of absorption and emission lead to a flux divergence. The downward flux of the surface is important in the land energy budget because it's a few hundred watts per meter squared. So it's actually comparable with the solar input, the downward long wave flux of the surface from the atmosphere. And the infrared radiation generally leads to cooling in clear air of the order of 2 degrees per day, and stronger cooling at cloud tops and warming at cloud base. So in clear sky, even when there's no clouds, there are some infrared active gases. Water vapor, obviously, which the model predicts. CO2 is a well-mixed gas that we specify as a constant over the whole atmosphere, but it can vary with year because of global effects of emissions. And nowadays we have a table where we look up the CO2 value based on the year. Ozone also, the table also has inputs for methane and N2O, which are other important gases treated constant in the model. Ozone is also important, it has its own climatology, it has a variability as well. So it is monthly variability, zonal, and pressure level variability of ozone. Less important for infrared, but more important for solar radiation. So the spectrum is divided into the two parts here. The solar part here, which we think is the input, and then the infrared, which is the output from the Earth. And the different gases, the total absorption is here, but different gases have different effects on different parts of the spectrum. So water vapor has a lot of effects both in the shortwave and the long wave part. Carbon dioxide mainly has a strong important band in the long wave part, 15 microns. This is the wavelength here. And then there's other gases which have some impacts on different bands. So I'm not going to spend a lot of time on the details of how these schemes work, but generally the long wave transfer we do in the model is we compute a downward flux and an upward flux, where there's absorption and emission in each layer, and the divergence of the flux is what leads to the heating tendency. The dt, the temperature rate of change, depends on the divergence of these fluxes. So that, but in the end, each layer you have a heating tendency from the long wave radiation scheme. The formula for the flux goes as it's emitted according to temperature, according to the Planck function, which is also a function of frequency, and it depends on the temperature and what gases are present and affect those frequencies. So we do this downward integration for the radiation at a given level. You're doing a downward integration of all the levels above it to give you that radiation flux, the downward flux at that level, for example. Similarly, for upward flux, you're doing an upward integration from the surface. This is a schematic of what those fluxes look like between the surface and the top of the atmosphere. That the upward flux decreases as you go up because of the temperature of the atmosphere decreasing. The downward flux increases as you go up, as you go down, because it starts at zero at the top, and then increases to a maximum at the ground. And the net flux is the dashed line, which you can see basically also increases as you go down, but the net flux is upwards. But this is what leads to the general cooling. Clouds are, of course, important for long-wave radiation. All schemes interact with resolved model cloud fields, allowing for ice and water clouds and precipitating species. Long-wave radiation is sensitive to particle sizes, which can come from the microphysics options in the model. Clouds strongly affect the infrared at all wavelengths, so they're considered gray bodies in terms of the spectrum, and are almost opaque to it. So long-wave radiation does not get far into a cloud before being completely absorbed by it. And also the emission from the cloud is just mainly from its surface at the bottom or top. Cloud fractions are also a function of height and also can be considered. So part of the grid cell can be clear and part cloudy. Then we go to shortwave radiation. So again, it's very similar to long wave in that we compute the clear sky and cloudy fluxes. Of course, the shortwave includes the annual and diurnal solar cycles. So the modeling computes the solar angle at every time step. And most schemes consider downward and upward reflected fluxes. It's primarily a warming effect in clear sky of 3.1 degrees per day. And it's an important component of the surface energy budget, of course, because of the diurnal cycle and the land surface heating. In clear sky, we also have to consider aerosols, pollution, or natural aerosols. The main gas effect in the troposphere is water vapor, as I showed. CO2 has a minor effect in the shortwave part of the spectrum. Aerosols can be considered in several ways in the Wolf model. You can specify the optimal depth yourself. You can use most people use a monthly climatology we have of aerosols globally. And you can also have interaction with Wolf Chem. If you run the chemistry option of Wolf, that can provide the aerosols instead of the climatology. Ozone is important for shortwave. Ozone heating by ultraviolet maintains a warm stratosphere. So you do need that if you're running a long simulation and you want your stratosphere to keep a reasonable temperature. It's important if model tops are above about 20 kilometers, where most of the warming occurs, or 50 hectopascals. And we have a month, as I mentioned, we have a climatology of ozone, which is by month in latitude and pressure. So in contrast to long wave, shortwave has no emission from the atmosphere, so it's simpler in that way that long wave you emit from each layer, Shortwave is basically just absorbing the layers. It doesn't have any, there's no emission of shortwave in the atmosphere or even at the surface. And all it does is reflect. But reflection is a complication because now you have upward and downward beams that you have to consider at the same time. So it actually requires a metric solution to solve for the shortwave radiation because you have to treat both upward and downward fluxes at the same time. At the surface, we can have slope effects for shortwave radiation. South-facing slopes, well, in this hemisphere, north-facing slopes have more solar radiation. So we can account for that. Radiation can also be separated into diffuse direct and direct components for solar energy applications, because the direct component is more efficient at producing solar energy. Diffuse component is basically the shortwave you get from the sky apart from the sun. There's significant amount of shortwave that come from indirectly from the sun. So that's the radiation part. Next I go on to the cumulus parameterization part. In models, you need a cumulus parameterization if your grid size is coarse, where it doesn't resolve. This is like the energy spectrum. So at 3 kilometers, you have updrafts where most of the energy for the convective cores exists. So think of these as vertical motion in thunderstorms, and that's at these scales. Often the model has grid sizes of 10 kilometers or more where they're not resolving this at all. You can have large eddy models which resolve it completely with grid sizes of 300 meters or down to 100 meters. Then you're resolving these convective cells individually in the model. So WRF is designed for this whole range of scales where we go from completely resolving the updrafts to completely not resolving the updraft. Cumulus parameterizations are needed only when you're not resolving the updraft. So for coarse grid spacings, cumulus parameterization schemes have been designed for grid sizes much greater than L. All updrafts and downdrafts are subgrid, and the 1D column scheme handles the subgrid vertical fluxes. So cumulus scheme acts just in individual columns where there's convection active. So for fine grids, resolve dynamics and microphysics are all you need to treat the thunderstorms. And so there you do not need a cumulus parameterization. You can resolve it with the model dynamics and the microphysics themselves. Cumulus parameterization, so when you have a coarse grid size, all this happens within one grid box. You have an updraft, downdraft. The updraft is taking boundary layer air to the top of the troposphere. Downdraft is often taking middle-level air down to the surface, driven by rain evaporation. There's entrainment, which modifies the updraft properties. So it affects the buoyancy of the updraft when it entrains air from the environment as it goes up. And around the cloud, there's compensating substance, which actually does most of the warming in a grid cell that has a cumulus scheme active. And then detrainment to the top includes cloud water that gets detrained out onto the top of the cloud. So for cumulus schemes, you need these for grid sizes that completely contain convective clouds, typically grid size greater than 10 kilometers. They redistribute the air in the column to account for vertical convective fluxes. The updrafts take boundary layer upwards and downdrafts take mid-level air downwards. The schemes have to determine when to trigger a convective column and how fast to make the convection act. I won't say a lot about this, it's just too long to go through, but this is basically the updraft and the downdraft is in the next slide. And this is a compensating substance, which is where most of the heating occurs. It also dries the environment at most levels. And here the downdraft is a downdraft which takes mid-level air downwards and actually cools and moistens the boundary layer, and it actually reduces the future convection. So in the end, the convection dies out because of the downdraft stabilizing the environment, but also because of substance drying and warming the environment, which also stabilizes it. So the convection is self-limiting, it eventually runs out of energy. Updrafts are driven by buoyancy, moist air goes to the upper troposphere, condensation. Updrafts have condensation, which converts to convective rainfall. Downdrafts are driven by convective rain and evaporation, and evaporatively cooled air goes into the boundary layer. Substance warms and dries the troposphere, and is the main warming effect in the column when this scheme is active. We also have shallow convection in various ways in the model. This is, by shallow convection, we mean non-precipitating shallow mixing, like cumulus clouds, which moisten and cool above the boundary layer. And this can be done by an enhanced mixing approach, as in some of these schemes, or a mass flux approach. Mass flux approach is like the cumulus scheme I showed before, where you're taking a mass of air from the boundary layer and depositing it at the top and having compensating substance. In the cumulus scheme, a mass flux approach is similar, except it's a very much shallower layer that the mass is being transported over. And shallow schemes may be useful at grid sizes that don't resolve cumulus clouds, which can be down to even 1 kilometer grid size. You may need a shallow scheme because you're not resolving the shallow mixing with the grid. There's also a convective gray zone, approximately 3 to 10 kilometer grid sizes, where updrafts are not well resolved. The grid column may not contain the entire updraft with compensating substance in this kind of grid size. Some schemes have scale-sensitive parameters to reduce the updraft effects of finer grid sizes. At 3 kilometers, updrafts are resolved well enough for no cumulus scheme. Dynamics and microphysics are sufficient to represent individual convective cells and downdrafts, especially mid-latitude strong thunderstorms, reasonably well resolved at 3 kilometers. Some may say tropical updrafts are not so well resolved by 3 kilometers, and you may even have to go to 1 kilometer before you resolve those. But to fully resolve the updraft dynamics may require less than a 300-meter grid, which is large eddy scale, usually very expensive to run this, and weather prediction models tend not to be down at this scale. The finest grids they have in weather prediction models are of the order of 1 to a few kilometers in some countries. Now we go to the surface part of the model, where there's three components. One is the atmospheric surface layer, one is the land surface model itself, and the other is the boundary layer scheme. The surface layer is called first. It provides what are known as exchange coefficients of heat and moisture to the land surface model. The surface layer also provides the frictional stress and the fluxes over water surfaces to the PBL scheme, because we don't have a water model, we don't have an ocean model. So the surface layer scheme can produce the fluxes from the water surface, which is relatively simple, but the land model can be fairly complicated because of vegetation effects. So that always does the land fluxes of heat and moisture. But note, the land model doesn't have to pay attention to momentum, it just deals with heat and moisture. So the surface layer scheme is a constant flux layer of about 1/10 of the PBL height of the order 100 meters in the daytime. The lowest model level is usually within that layer, so when you're on wharf, you have to have the lowest model level below 100 meters to make this work well. Typically, we have our lowest level between 10 and 50 meters above ground. Therefore, the lowest level variables can be used to derive surface fluxes via similarity theory. If the lowest level is within the surface layer, the lowest level values of the model wind, temperature, and moisture can be used to derive a surface flux using similarity theory. Similarity theory has U star, the heat flux is given by Cp, rho Cp, U star theta star, where U star and theta star are values that are constant within the surface layer, which is the lowest 100 meters. And so you can compute, you can compute them from the values at the lowest layer, and it'll give you the fluxes. We also need a roughness length. That depends on the surface type, or for water surface, it depends on the wind speed. But the roughness length is basically high for forests, for example, in urban areas, and low for grassland and flat areas. Similarity theory uses the idea of the wind, for example, has a low profile that's proportional to U star, and U star is given by the lowest level wind divided by a function of the roughness length in neutral conditions. This gets modified for stable or unstable conditions, but the basic simple log profile is the neutral state. And so you get U star by this kind of formula. Similarly, theta star has a similar formula, and all derived from the lowest level values. And then you you have U star and theta star that you would need to compute the fluxes. And a similar thing happens for this heat is U star theta star, moisture is U star Q star, momentum is U star squared, and these are the formulas for those similarity variables. And remember, these are constants in the layer. Then we have the stability modification, which are these psi functions. They're a function of Z over L, which is a function of the surface stability and fluxes as well. Delta refers to the difference between the surface and the reference level. So here's theta ground minus theta the lowest level, for example, and 0 to the reference length. You can see that therefore you need the ground temperature before you can compute the flux. But before you go into the land model, you don't know the ground temperature. So the exchange coefficient is what goes to the land model, which is the proportionality between the heat flux and this delta theta. We don't know delta theta yet because the land model is going to produce that, the ground temperature. But it has to obey this equation, and it'll produce both the heat flux and delta theta, given this CHS as input. CHS from the previous formula is given by this. So it's a function of U star, which is the wind speed, and reference length and stability function. The land model itself, we have several processes. These are the fluxes represented here. The land model will produce a sensible latent heat flux. It's also driven by the net radiation as inputs. And then there's a ground flux into the soil. So typically we have maybe 4 soil layers. And then there's a soil thermal diffusion within the soil, and also a moisture flux, which may be drainage of water from the surface down into the soil. And then about 2 meters or 3 meters below ground is a layer you can consider constant temperature, because mainly the annual mean temperature is more or less fixed at about 3 meters below ground. So we use that as a lower boundary condition because that doesn't change through the year. And for the water, it's much simpler. We just use water, you have sensible latent heat flux, and it provides an upward long wave flux. The land surface itself has to deal with a lot of processes, especially complicated by vegetation. So it's dealing with precipitation, which goes into the canopy as well as directly to the ground. We have the vegetation itself, for example, trees, which have a root zone, and they can take soil moisture from deeper layers and transport them out into the environment. So you have to consider this non-local transport of moisture by trees, for example. Then we also have to deal with snow cover prediction in the land model, because the snow melts and accumulates, and that's all part of the land model equations. And meltwater runoff, we have 2 types of runoff, the surface runoff and the deep runoff. The surface runoff, the model is we don't have a hydrology model within WRF, but there is WRF Hydro, which is an external hydrology model, which will take the runoff and put that into rivers, for example, both the surface runoff and the deep runoff. Without a hydrology model, these runoffs are just disappearing from the grid column, which is the more normal case of when you run WRF. The runoff just goes away. We assume it goes to rivers and then out to the ocean. So this is an illustration of the kinds of complexity you deal with in the land model. So the land surface model is driven by the surface energy and water fluxes. It predicts the soil temperature and soil moisture in the layers. It predicts the snow water equivalent on the ground and may have a multi-layer snowball. It may predict canopy moisture and temperature, canopy being at the tree level. There are also vegetation effects like evapotranspiration, the root zone, trees. The soil effects, drainage, thermal properties. And urban, we have urban models too, which exist for more sophisticated representation of what we call the urban canyon, which modifies the radiation within urban areas. They often have a separate treatment of walls and roofs and roads. and allow for the energy budget between those two components. And there's also an anthropogenic heat source within the urban areas. So we have those urban options. You can run a simple urban scheme where it's just another land use type. We can also run a full urban model, which includes some of those extra effects. So now we'll go to the planetary boundary layer. The boundary layer, this is a PBL top. It's about 1 kilometer, for example, during the daytime. You have multiple layers. Typically in the model, in the boundary layer, we have at least 5 to 10 layers below in the lowest kilometer to try and resolve the boundary layer. As I mentioned before, we have the surface layer here, but then you have multiple layers above. There's mixing both between neighboring layers or non-local mixing, which you can think of as thermals that rise from the surface due to the surface heat flux. The boundary layer lower boundary conditions, sensible heat flux, latent heat flux, these go into the boundary layer and then have to be distributed through the boundary layer by those fluxes. And some of these being non-local fluxes make it a complicated process for a model to deal with, because normally the model deals with diffusion between neighboring layers. But you need a boundary layer scheme to allow for things like thermals, which transport energy from non-neighboring layers. Similar to the cumulus parameterization that I mentioned before, when you're dealing with non-neighboring transports, you have to have a parameterization scheme to deal with this. Friction is also an input to the lower. It's like a momentum flux, which is also modified by the surface. So there's basically a loss of momentum into the surface that the boundary layer scheme has to treat. So during the day, the boundary layer develops from a stable layer at night to a daytime boundary layer. This is sunrise and sunset here. And after the sunset, basically the boundary layer collapses and you have a weak residual mixed layer, and then the stable layer develops overnight again. Typically during the daytime, you have a well-mixed wind, temperature and wind profile, and you have a slight, reasonably mixed scalar profile of moisture. And then there's typically an inversion above it, and then the free atmosphere above that. Surface layer may have a slight supraadiabatic layer here. So this is where the temperature actually increases as you get closer to the surface, but most of it's more or less neutral. So PBL schemes come in a couple of different types. We have non-local schemes and we have turbulent kinetic energy schemes. So non-local schemes, we treat the flux. This is the flux in a given layer. It's a function of the local gradient, like in diffusion, plus there can be a non-local term like these thermals, the deep one, the blue arrows here. So we have to treat both these types of terms. It's a combination of a local mixing and a non-local thermal. This is why they're called non-local schemes. And we can either treat these with a mass flux term or what's known as a counter gradient gamma term. So there's two ways of treating that. One is just a mass flux, as similar to cumulus schemes, or as a counter gradient term, which is just an additional term here representing a non-local flux in a simple way. So we also have TKE schemes, turbulent kinetic energy schemes, where you solve for turbulent kinetic energy in each column. The source terms of buoyancy and shear. There's also dissipation and vertical mixing of TKE. And TKE, which we call E usually, and a length scale are used to determine the K coefficient for local vertical diffusion. So these schemes are more for local schemes, local vertical mixing. And you also need the stability to determine this K. So the more kinetic energy you have, the more turbulent kinetic energy you have, the stronger this mixing is. And that's the idea. And buoyancy and shear produce this turbulent kinetic energy. So schemes differ most in the diagnostic length scale computations and how S is calculated. So with the non-local schemes, we first diagnose a PBL top, either through a stability profile or Richardson number. We specify a K profile in a simple way. This k is often like a cubic function. And then this has got the gamma term that I mentioned before. It's just specified as a function of the surface heat flux mostly. And so you can see that even when there's no vertical gradient of theta, there's still a vertical flux due to the gamma term. So this allows the boundary layer to develop a neutral profile or even a slightly stable profile because of this term. The mass flux approach is at the bottom here, which is an additional updraft flux, also known as eddy diffusivity mass flux scheme, where you have the normal diffusion term here again, but now a separate mass flux term, which depends on like the thermal temperature minus the environmental temperature, and it has to determine the mass flux to using this term. So now we get to PBL schemes in the gray zone. So now this is a similar diagram to before, but now the scales are different. Here we're dealing with thermals. So the turbulence containing scales are of the order of 1 kilometer or less. These are the large thermals arising from the surface due to the heat flux. And you're either resolving these or not. Most often in mesoscale ones, we're on this side, but we're not resolving those, so you need a PBL scheme. When you're on the other side, so here you need the PBL scheme for the grid size much greater than L. All that is a subgrid, and you need basically a one-dimensional scheme that does the subgrid vertical fluxes. So then you have the gray zone, and then you have the fine grid spacing, which is typically 100 meters or less, where you have large eddy schemes, which is designed for this. In this, you turn off the PBL scheme, and everything's done by basically a diffusion type scheme, because everything is now local fluxes. You're resolving the thermals, so you don't need the non-local vertical flux term. And it's basically a three-dimensional turbulence scheme. So horizontal and vertical mixing are now unified within the LES scheme, whereas they're kind of separate in the PBL scheme, where you have vertical mixing done by the PBL scheme, and horizontal mixing being done by the diffusion scheme. So this kind of unifies the fluxes into one three-dimensional turbulence physics. So as I mentioned, there's a gray zone for sub-kilometer grids, where neither PBL or LES assumptions are perfect. Some schemes are being designed for this range with scale-sensitive weighting functions, for example, Shinhong PBL and 3D TKE schemes, where they can kind of transition from being more like a PBL scheme to being more like an LES scheme within this range of like 100 meters to 1 kilometer grid size. Other PBL schemes work in this range, but will not have the correctly partitioned energy fluxes, or resolve scale versus subgrid scale fluxes. But they'll give reasonable looking profiles anyway, even if they're not giving you the correct energy balance on the different resolved or unresolved scale. They'll give you a reasonable developmental boundary layer scheme, so you can use a PBL scheme, for example, at 500 meter grid size. In the model, we also have turbulence and diffusion active anyway. There's horizontal and vertical diffusion above the PBL. There's still vertical diffusion. Most often the PBL scheme also handles the vertical diffusion in the free atmosphere, but it's basically a simple term with a K coefficient and the vertical gradients. So at the LES scale, we have a couple of options involved to enable this. For grid sizes up to about 100 meters, LES is a preferable choice. LES treats the turbulence three-dimensionally instead of separately vertical and horizontal diffusion schemes. Explicit vertical diffusion replaces the PBL scheme and accepts the surface fluxes from the surface physics. So the heat flux and moisture flux and momentum stress are all inputs to even the LES scheme. WRF has TK and 3D Smagorinsky options for subgrid turbulence. So you'd set a boundary layer option to 0, and then you choose the method, either TKE or Smagorinsky with this KM option. So it can use you can use a PBL scheme on the outer domains and LES on inner domains. If you're doing nesting and you have grid sizes across the gray zone. So with turbulent kinetic energy, now we're doing turbulent kinetic energy for both horizontal and vertical mixing. I mentioned before the PBL scheme, which does just vertical mixing with its own turbulent kinetic energy. Now we have basically a three-dimensional effective turbulent kinetic energy. Both KH, horizontal and vertical mixing, depend on the TKE. And again, there's similar production terms and dissipation term. And these depend on the shear production term depends on basically a function of the wind gradients, which are these D terms, deformation terms. And the buoyancy term depends on n squared, the stability, Grove-Leiter stability frequency. And then there's a dissipation term, which is proportional to the TKE to 3/2. So K, as I mentioned, is computed directly from the deformation. These are basically horizontal and vertical gradients of the UV and W winds. Next we go to microphysics. So the model, microphysics has to deal with all the clouds in the model, various kinds of clouds. It could be ice clouds, cirrus type clouds, it could be deep convective clouds, it could be cumulus or mid-level clouds, which arise from radiation, for example, or stratocumulus, as often seen over the ocean. So we have to deal with all these. They're formed by radiative dynamical, for example, mountain waves, dynamically forced clouds, or convective processes. The model only considers grid scale averages for clouds, so it will not resolve fine scale structures which are smaller than the grid size. We have multiple types of scheme involved, different levels of sophistication. There's a warm rain scheme, which is really only good for idealized cases because it has no ice. Most parts of the world, you do need to consider ice clouds at some level. So then you have the simple ice scheme, where you only still need 3 arrays, but we classify the particle type based on the temperature. So now we have cloud water, rain, and vapor, but also have cloud ice and snow. You can go to mixed phase ice, which now needs 5 variables. The cost of the scheme is mainly proportional to the number of variables, so the purpose of the simple ice scheme is to reduce the cost. By having the mixed phase, you can now have snow that melts more gradually as it falls below the freezing level, and you can have supercooled water as a cloud can go above the freezing level. So that's important for some applications to have supercooled water and snow melting more gradually. Then you have the convection resolving kind of scheme where you need graupel in addition to the other variables. This is more dense ice particles. In the extreme case, you can go to hail. And you need these denser ice particles to fall out closer to the updraft and give you a more reasonable intense rainfall that you don't get if you just leave everything as snow that gets transported away from the updraft. There's another type of scheme called Kessler-Ferrier, which is vapor plus a combined species. So it only has 2 arrays. It's very simple, but then you have to have partition arrays between these, which are not interactive. So multiple processes you're dealing with. Of course, there's latent heat release, condensation, evaporation, deposition, and sublimation, and freezing and melting. There's several particle types. There's the cloud water, raindrops, ice crystals, snow, graupel, or hail. And the total mass also contributes to liquid loading in the dynamics. And the processes are aggregation. Aggregation is when rain falls through the cloud and aggregation is when ice turns into snow by collecting ice crystals together. Accretion is when rain falls through the cloud and collects cloud water. Autoconversion is when cloud droplets turn into rain droplets by growth and or accumulating together. And then sediment riming. Riming is a mixed phase process where liquid and ice interact to produce these denser particles. And water and ice saturation, or sedimentation, it's important. Most particles have a fall speed. I'll talk about that again next slide. But also important to note that water and ice saturation differ from each other. At cold temperatures, the difference can be as much as 40%, minus 40 degrees Celsius. And ice saturation is lower than water saturation. So you can be ice saturated but subsaturated relative to water. So these particle types, cloud droplets are tens of microns in size, are condensed from vapor at water saturation. Cloud condensation nuclei are fixed or variable in the model, and they're either specified or come from Wolf-Chem. Rain is of the order of millimeters in diameter and forms from cloud droplet growth. Ice crystals are tens of microns and form from freezing of droplets or deposition onto nuclei, ice nuclei, which are assumed explicit or can be dust particles in parameterizations that allow for you to predict dust particles. Snow is of the order of hundreds of microns in size and forms from the growth of ice crystals. And then also these ice crystals aggregate together, they collect together to form these aggregates of snowflakes. And then graupel and hail, millimeters or centimeters, and form and grow from mixed phase interactions between water and ice particles. And then precipitating particles are typically assigned to an observationally based size distribution. So the size distribution is this: there's a diameter here, and the number of particles in each diameter range is here, and it's basically a logarithmic number of particles. And you can either have a linear function, which is the Marshall-Palmer distribution, or you can have a gamma function, which has a maximum at some diameter, maximum number of particles, and goes to 0 at very small particles. So the schemes are more often these days use a gamma distribution. That's given by this function here. So the number is just a function of the diameter. And there's the other parameters, alpha and lambda. Lambda itself depends on just the number of, or the mass concentration of the rain, for example. These are other relations that are used in the model. The mass of the particle depends on the diameter cubed for liquid at least. And then the fall speed depends on the diameter as well. And then you also can you need a mass-weighted fall speed because you have a size distribution. So you have a mass-weighted fall speed, which you have to compute by integration. So we also have single and double moment microphysics schemes. Single moment schemes have one prediction equation for mass per species, for example, what we call QR, QS. These are the kilograms per kilogram of that species. Typical values are 1 gram per kilogram of rain, for example. Heavy rain would be 4 or 5 grams per kilogram. Particle size distribution being derived from fixed parameters, for example, the N0, which could be a given parameter. Double moment schemes have an additional prediction equation for number concentration, so it's the number of particles per kilogram. So when you know the number of particles and the total mass, that gives you like a mean size. So it's another degree of freedom, and the NR, these numbers are also predicted variables. These allow for the aerosol effects, for example, where cloud number concentration increases when you have more aerosols or more pollution. So it allows for the cloud droplets to be smaller in polluted air, which affects the microphysics. The microphysics fall terms, the schemes handle fall terms for particles. Usually everything except cloud water has a fall term. These numbers are given here, the typical fall speeds. Even ice crystals have a fall speed of 0.5 meter a second. That's important for depleting cirrus clouds in a reasonable length of time. For long time steps, such as mesoscale applications, our time step is 60 seconds, and the fall speed is 5 meters per second. So drops may fall more than 1 gravity level in a time step, which is numerically unstable. So we have to treat these in various ways, which include either splitting the microphysics time step so that a particle can fall only 1 grid level per time step, or a Lagrangian method, which allows it to be treated in 1 time step. So this happens at coarse resolutions where the grid size may be about a minute. Then there's aerosol cloud interactions with radiation. The model can handle aerosols either through chemistry or specified. And the aerosols can contribute optical depth to the radiation directly for clear sky, but also can contribute to the microphysics through the nuclei on which the cloud or ice form. So WRF has capabilities in this direction, especially with the Thomson microphysics option, which allows for this full interaction of aerosols with simplified aerosols. Even without running WRF chemistry, you can have this interaction with Thomson. With chemistry, you can get this interaction, but you need the full chemistry model, which is very expensive. Yeah, just for completeness, I've added the show and convection also contribute cloud fractions to the radiation. And also the microphysics produces the cloud amount, but also the effective drop sizes or ice crystal sizes, which the radiation also interacts with, because smaller particles have more radiative effect for a given mass, total mass. So these are the physics I've gone through. They all interact with each other in some ways. The cumulus schemes detrain cloud into the microphysics. Both the cumulus and microphysics produce rainfall contributions to the surface. We call them convective rain and non-convective rain. So in the WRF output, you have two types of rain that you have to add together. If you're at fine resolution, you're not running a cumulus scheme, so all the rain would be in the non-convective part. The cumulus scheme can also provide a cloud fraction to the radiation. The radiation provides the fluxes, the net radiation to the surface, which also then provides the surface fluxes to the PBL scheme. So as you can see, we have a lot of interactions in physics. We also have a capability we call nudging in WRF, which allows you, when you run long simulations, to keep the model roughly on track. It's used for several methods. Dynamical initialization, where you have nudging before your forecast starts. Four-dimensional meteorological analysis, where you nudge through a whole period. It kind of nudges the model towards the analyses. So you're getting maybe a high resolution time and space analysis. The model is used to interpolate basically with physics and dynamics to give you better resolution than the original analysis. So this is often used in air quality applications, where they want to have a four-dimensional data set for air quality modeling to run offline. We also have spectral nudging, which is often used in regional climate applications, where you just nudge the larger wave. If you run a continental scale grid and you want to run for years, many years, you'd like to keep the weather systems on track. So you use spectral nudging to nudge the large scale waves and keep them on track in phase with the real ones, even far away from the boundaries. Usually if you have a small domain, the model is well enough constrained by the boundary conditions, but if you have a continental sized domain, you may need to have nudging to keep things in the right phase. If you're nudging, and you only nudge when you have analyses that you nudge towards. You don't nudge if you're forcing the model with a GCM, for example. So now I'll go into the MPAS part of the talk. I think I still have plenty of time. It's only a short part. I'll talk a bit about what MPAS is. So MPAS is the next generation model after WRF. WRF is a regional model. It had a global application, a global capability, whereas basically a latitude-longitude grid that needed polar filtering. MPAS gets around these problems by having an irregular grid, which is based on, typically it'll be hexagons, and they can have, you can also have variable resolution, but you can have a uniform resolution, which is hexagons around the sphere except for like 12 pentagons. And so MPAS is run in both modes. It's run either with a variable resolution or with a constant resolution. But the benefit of this type of grid is very uniform grid globally. You don't have to worry about the polar area having small bit sizes, for example. Every part of the domain has the same resolution. This is, of course, a very coarse grid, but the model would typically run with much finer resolution than that. I won't say much about these equations, but the dynamics is actually very similar to WRF. It's a fully compressible, non-hydrostatic set of equations. So it allows for sound waves as well as non-hydrostatic effects. It's a prognostic equation for a couple of variables. Here we're basically, it's a height coordinate. North is a pressure coordinate, pressure-based coordinate, terrain following. MPAS has gone back to a height coordinate, also terrain following. It's a generalized height coordinate. So all the grid points are fixed in space, whereas in WRF they kind of float based on the surface pressure. So the top in MPAS is basically a fixed height, whereas in WRF it's a fixed pressure. The momentum is treated with what's known as a vector invariant equation set. Momentum is special on a hexagonal grid because you don't have the same concept of zonal, meridional wind. You have to have a local wind, which is just defined at that grid cell. So the wind component you're predicting is actually the normal component to each grid cell. So you don't have your normal U and V component. So this equation looks quite different from the momentum equation you might be used to. Plus we have these other terms which are related to the other component of the Coriolis term, going as cosine of the latitude, and this type of term, which is the curvature term related to the curvature of the Earth. Similarly with W, you have the other component of the Coriolis term, and you have the curvature term. So the equations may not look so familiar, but the dynamics is very similar to WRF in that sense. So it's the same equations, just put into a different form. Thermodynamic equation is for moist potential temperature, theta m. Theta m is defined here. It's not quite virtual temperature, but it's something very similar to that, where RV over RD is like 1.61, whereas for virtual temperature it might be 0.61. This is just used for convenience because theta m is then closely related to pressure, which is pressure is also a diagnostic variable from theta m. And we also predict the height field in this model. So the MPAS, we call it MPAS atmosphere because there is also an ocean model being developed, which has a similar type of grid. It's mostly hexagons, some pentagons, and heptagons. Cell centers are centers of mass. The lines connecting the cell centers intersect the cell edges at right angles. So there's very specific geometric properties this grid has to have for this to work. For the velocities to actually mean correctly the normal velocity, for example, and for the fluxes to balance. So the lines connecting the cell centers are bisected by the cell edge, and the mesh generation uses a density function. Mesh generation is quite a complex process. It takes a lot of iteration to create a mesh that's not uniform. So we have ways of doing that. But you can also reuse existing meshes and rotate them to your area of interest. So it's a C grid, which means the velocities are carried on the cell edges. This is basically a typical grid cell. So we see the velocities here are normal to the cell edges. These are the only velocities the model predicts. It doesn't predict any other component except for the normal velocity. So at each grid cell face, you have that velocity in any of these directions. And these are the ones you need for the fluxes of all the variables between cells. So the cells are also identified by a single index. It's not like an I and a J index. You just need one index. But then you also have to keep track of what all the neighboring cells are, so you know which ones are interacting with which ones. So it's much less straightforward than just I plus 1 and I minus 1 and J plus 1, J minus 1 for neighboring grid cells. It's more like I and a function of each cell face is the neighboring index. So they have to keep track of neighboring indexes at each face. Or vertical coordinate is also a bit different from WRF. Basically, the vertical coordinate they use a smoothing function of height. This is documented in Clem's paper from 2011. So each level is smoother than the one below. So you have the complete complexity of the train at the bottom, but then it gets smoother and smoother until it becomes flat at some height above that. So that's given by those equations. The time stepping is very similar to WRF in that we do the physics first, and then we have what's called the one-color third order scheme, where you go a third of the time step first. That gives you new terms you can use in your advection, which then go to a half a time step. That gives you the center of the time step, which you finally do for your full time step. So now you're advecting variables defined at the center of the time step, so it's more centered in time, but you have to get there by doing these first two iterations. So you're doing basically 3 advection computations per time step. But you only compute the physics once. That goes as a right-hand side term, a fixed tendency term into these other steps. The things that change in these steps are basically the variable itself and some of the Coriolis terms, etc. And then at the end of the time step, we also have these small steps for the sound wave modes, where we update the velocities and pressure. And then at the end of the time step, we finally do the microphysics at the end. So some examples of MPAS use. It's been around since 2010. We've had this model. So it's 10 years. It's becoming more of a community model now. So these are some of the early tests. This is showing the following coordinate, the new version plus the old version, which is more like the WRF type. The WRF type maintains the topography all the way to the top to some extent, whereas the smooth type flattens before you get to the top. And the results are very similar, but you can have less noise with this type of coordinate because it's flatter at the top, which tends to lead to less noise at higher levels. In WRF, we now do have a hybrid coordinate, which also can have a flat upper levels. So WRF also does have this capability of going flat at the top, but by using a different method from the smoothing. You can see this example was done in South America. That's the Andes there in this test case. We also do convective storm simulations with MPAS. You can go from global scale. This is a 3 kilometer MPAS simulation. So the coarse resolution, you have this, and then as you get to finer scales, you're resolving individual thunderstorms, and then this is the thunderstorms at the finest scale. 3 kilometers, you're kind of resolving the splitting supercells, for example. Here, this is the cold pools, the theta at the lowest level. So all this is resolved well when you get, and this is the cold air behind the front. All that's resolved well and on a global scale. It's expensive to run this type of thing. Also taking part in the hazardous weather testbed spring experiments. Here's a couple of examples showing the sensitivity to microphysics. The real rain was in blue. The model rain dial cycle was not correct. It's giving rainfall, it's giving the correct mean, but not the correct dial cycle. Changing the microphysics actually helped a lot. This is going from WSM6 to Thomson. The Thomson scheme does produce a much better dial cycle over the US. I think other parts of the world you find it's the other way around, where WSM6 does better than Thomson, because Thomson's mainly been developed over the US continent. And some verification here. This is basically the different thresholds of rainfall. The bias is in blue, so it's close to 1, which is good for all the thresholds. This is the threat score, which is the skill. So day 1, the skill is quite high, 0.4, but then drops obviously as you get to day 5. But it's showing the 15 to 3 kilometer mesh verifies reasonably well. This is for 2 different years, 2015 and 2016, 31 forecasts. Another initiative where MPAS is taking part is called Diamond, which is an international initiative with, I think, led by the German group, Max Planck, but also Japanese and American and British and French, and the European Centre participants. And these are just multiple global models being run at cloud scale. So in the MPAS example, it's being run at 3.75 kilometers, and they're all run for 40 days with the same initial conditions to compare them. So it's a comparison project. And they've done a second one now since then, which is a winter period. But this is 40 days in the northern summer. This is a sense of the outputs, and they did a lot of comparison between these models to see how realistic they all were at cloud resolving scales. For example, this is the tropical storms observed, and with, let me show the MPAS, I won't show the other ones, but the MPAS has given you reasonable tropical storms. That being 40 days, you don't expect the real ones because you're beyond the forecast limit range of 5 to 10 days for most of this period. So it's just a climatology, effectively, of tropical storms. The sea surface temperature is still specified, though, so there is some deterministic aspect to the boundary conditions. So the sea surface temperature does vary over this period, so it does help the storms to develop in the right place, roughly. This is a statistic for tropical cyclones, which is important, which is how the wind and the maximum wind and pressure are related to each other typically. So the black ones here are the observed wind pressure relation, red is the model. So they ran then past the multiple grid sizes, and so the wind pressure relation gets better and quite realistic as you get to 3.75 kilometers. So it's showing the tropical cyclones. Notice these are very low pressures here, because these are tropical cyclones, and we're resolving them with the model. And the winds are strong, 140 knots, that's 70 meters a second at the extreme end. Let's see if this works. This is an animation of the So it started with a very low resolution analysis, and you can see it immediately gives you high resolution. And this is the reflectivity as well as a simulated satellite picture of the upward long wave radiation. So there's a couple of, obviously you see a couple of tropical storms here in the Atlantic. And as you see, you start with a low resolution, it's hard resolving anything, and it develops a lot of these structures in a model that look quite realistic. And some verification was done of MPAS compared to the other models, and it's doing quite well in general in terms of how it's treating, especially tropical storms in a climatological sense. Yes.
Just curious, when you say 3.75 kilometers, you're saying regular?
Yeah, over the whole globe,
Okay.
which is a very expensive simulation. So they only ran 40 days because it's so computing costly. You can't run for them. Yeah. I forgot how many million points it is, but it's maybe tens of millions of columns. Okay, so that was, I think that's the talk. MPAS has been developed by Bill Scammell and Joe Clem at NCAR, and the other names here, like to do that software engineering. A couple of people developing the physics. I'm also participating in the physics. Mainly the physics in MPAS is coming from WRF. We've chosen some of the more used options in WRF and put them into MPAS. And we're trying to keep shared physics in the future where both languages share the same repository for physics, and we're going in that direction for the next release of WRF and MPAS. NCAR is supporting both these models. So far, the user community for MPAS is much smaller because it's less easy to use. They have tutorials twice a year now, and so WRF has tens of thousands of users. MPAS may have maybe 100 or so currently. Um, because WRF can do a lot of what MPAS does. And there isn't a large community for global models. We found that out before, that the university community tend not to want to run global models, they've got much use. Because climate models, for example, are global, but they're run in one center, and the university community just uses the outputs. So it's hard to see the community for a global model, but MPAS is there. And MPAS also now has a regional option, which just became available in the last year or two. So we expect the number of users to increase. People who are starting a new model should probably start with MPAS if they're not using WRF already. People who are using WRF, it's fine to continue because it doesn't do any worse than MPAS. So it's hard to tell them to transition. But if you're starting with a new model, MPAS is the one that's going to be developed more in the future. And we're adding options still. There's still some options it doesn't have. Okay, that's it. Thank you.
Thank you very much, Jimmy, for your talk. It's interesting because I have a lot of students, grad and undergrad students. In general, in the course, we see everything about meteorology, radiation, microphysics, PBL. Separately, in the model, we need to put all together, and this model needs to be fast, needs to be stable, and needs to be precise. So it's a hard work. Thank you for your talk, and you are open for questions.
Hello, Jimmy. Thank you for your presentation. And very end now, we're talking about, if someone is starting to choose a model, maybe should go for MPAS. I wonder how much, but at the same time, we have a lot of users around the world with WRF model. Do we still see, say, funding-wise, development of work still keep going on for in the long run, or do you see that you could see in a given moment the full transition to MPAS?
We think the WRF users, there will always be many more WRF users and MPAS users, so we don't want to abandon them. So there's still a forum. WRF has a forum where you can ask questions, and we still have people who help with answering questions for WRF on that. And currently, most of the questions MPAS can be asked also on that forum. Most of them are still from WRF, and so we plan to keep supporting WRF in the sense of user questions. In terms of development, it's slowing down, but we're still getting new schemes. We're currently at version 4.5, and next April we'll have version 4.6 that will already have maybe one or two microphysics options. So there's still things going into WRF, but we're also trying to have the concept of shared physics, so that things like YSU scheme and NOAA MP land model will be shared between the models with the same code. So we're trying to share physics to allow any development in one to be automatically in the other. So we don't plan to turn off WRF support, and people always ask us. And we try to assure people it's not going away.
I do have some questions from people from the chat and internet. So it's basically the same. There's this Danilo Sidin. He's a young meteorologist, and he is asking exactly what you answered. I'm starting before, or I should go directly to MPAS. What do you think about the future?
They do tutorials for MPAS. They probably have that. They have tutorials for MPAS now twice a year, similar to WRF. I think those are in the WRF ones are in the summer and winter, and theirs are in the spring and fall. And there's like a week course where you can learn MPAS. And the pre-processing system is very similar for both models, WPS type system. So they're both usable, and encourage new people to look at MPAS.
There is another person, Robson Robson Passos. He did two questions. I will condensate this. He's trying to use worthless for renewable energies, and he's asking if there is any intent to go forward work on GPUs to reduce computational cost, or if you're going to do any effort in the future to have work running, better running in GPUs.
There isn't any NCAR effort. There is an MPAS effort with GPUs. So far, it's not as efficient as they hoped. But that's the only direction. But there is a commercial company that has WRF on GPUs. They don't give the code. They just give you the executable. And you have to pay. But but yeah, we are aware that a lot of people are going in the direction of GPUs. There are many ways of going, and we still think that's not stabilized as to what the best route to go to GPUs is. Whether you have to rewrite your code or you can just use directives in the code. There are both those available. It's much easier to just add directives so the Fortran code still looks the same. But some people go and change it to C++ and other languages to get it to work on GPUs, and that's a much harder thing for physics, and we don't really plan to go in that direction. But then there's, in the end, there'll be maybe some compilers which can convert Fortran code to more efficient GPU type code. The European Centre is going in that direction. So there's still multiple methods, and we still have got a plan for GPUs. You want to have a couple of questions? LES, it's interesting. LES, we don't, and MPAS doesn't yet have LES. I worked on MPAS LES, which currently now works for only idealized applications. So it's like a flat plane hexagonal grid. That LES works. It's the same scheme we used in WRF, only put on a hexagonal grid. So MPAS doesn't yet have the LES capability, but WRF, of course, does.
And I have a last one from myself. When you showed, I was curious, when you showed the direct interaction between physical schemes, there was no direct connection between PBL schemes and convective schemes. But when doing my simulations in Amazon, where there is a weak synoptic environment, like forces, large-scale forces to produce storms, I saw a lot of storms during the night being killed by the PBL schemes. So I need to change the PBL schemes to have more mixing and then initiate convection. So how there is or there isn't this connection?
Well, okay.
Right.
So what I illustrated was only direct connection. So if there's an output from the PBL scheme that goes into a convective scheme, I would have listed it. There's no output directly. It only interacts via the atmosphere. What it does to the atmosphere is stability profile. So that's why it's not listed. So it doesn't mean there's no interaction. Through the atmosphere. No direct interaction. It just happens through the atmosphere.
More questions? Of course.
I'm just curious if we already have any paper coming out from the diamond interim comparison projects. I'm curious about the comparison of MPAS with other models.
I don't know what the status is, because as you saw, that program started in 2018, and they're doing a second one now, 40-day period. So Falco Judd is the person to look forward to, DT, he's at NCAR. But also Bjorn Stevens is the leader of that project. So they have an intercomparison paper, but I don't know the status. It should be. It's a very big project.
Good. All done. So thank you. Oh, sorry. One more.
One more.
We did some simulations trying to understand the stratospheric and tropospheric mass exchange using WRF. What do you have to say about MPAS? How it's going to be this top upper level interaction will be possible? Or?
I I know that's an area Bill Skamrock has been very interested in. It's the vertical resolution needed for this type of thing to be done correctly. And he's done, since the people published it, he's at least had conference papers on sensitivity to vertical resolution and what you need to converge the result, and it's down to like 100 or 200 meter vertical resolution that he's found you need for NCAR'S to do that. And Wolf would have a similar target resolution. There's no reason NCAR'S would be different from Wolf, but I think he's done that work with NCAR'S, and these are the kind of thing. Mainly he's looking at vertical resolution and gravity waves in the stratosphere, breaking things like this. So there's a convergence of solution down at those height sizes. Less than a few meters. That's all I can say on what he's done. If you look for his, he must have some conference papers on what he's done. That's come out.
Okay, Jimmy, thanks once more.
Okay.
And I would like to invite you for some snacks at Gruma Lab. So at our lab, some snacks. And thank you, Jimmy.